start with first introduction about yourself. Yeah, thank you very much. Thank you very much. So let's start with first presentation of Mr. Marc. So Mr. Marc Korevar received his PhD degree from the University of Technology in 2015. So for his research on applied physics, since 2015, he works at Donen in research and development. There he is involved in the development of new solar energy detector, their calibration and radiometry. Kip&Zonner is a leading manufacturer of measurement instruments for meteorology and solar energy. So Mr. Marc will present artificial intelligence measurements in irradiance for solar photovoltaic and solar CSP. So Mr. Marc, please, the floor is yours.
Thank you very much for this introduction, and thank you very much for organizing such a nice workshop on this topic. And I will say some words on irradiance measurements and what we have sort of researched. What can AI do in these cases? And I will also touch on PV plant monitoring and AI related to that. I will first say a few introductory words about the company that I'm working at. It's called OTT HydroMet, but Kip&Zonner is part of it. And Kip&Zonner makes the solar irradiance sensor and atmospheric science sensors for meteorology and solar energy. And we have also got sister companies such as Luft, which make the weather stations and other meteorologically related sensors. And we also have Meteostar, which is making software for weather forecasting. And yeah, I work for Kip&Zonner in the Netherlands. So when I was asked to say a few words, I was thinking, okay, now what is from the perspective of the company where I work important? Now what can we contribute? And then we thought that the end goal is that we can have stable and optimal energy production in a PV plant or in a CSP plant. And for this, fault detection and good maintenance is important. And from a company as OTT HydroMet, we think that we can help and support this by making more accurate measurements and available to the analysis that there is. So yeah, can we make irradiance measurements which operate better with artificial intelligence? And if we measure things, which measurement parameters are important for AI in PV plant analysis that will enable fault detection and good maintenance? So first, I will talk a little bit about the irradiance sensors and some of the experiments we did and how can AI help improve that. And we believe that when we are able to measure irradiance more accurately, we can also improve the capability to detect that something is happening in the plant. And the second part will be a PV plant case study where we will look at, okay, which kind of measurements are beneficial for AI in the plant. And then I will wrap up with a summary. So I will start with one of the products that are made by Kip&Zonner. It's called a pyranometer. And this comes from a Greek word, or Greek words, pyra, ano, metreo, which stands for fire having measure. And it can be used to measure the global horizontal irradiance when mounted horizontally. You have variants which use a silicon diode for measuring the irradiance, or the thermopile, the higher classes of pyranometers. And often in a photovoltaic plant, you see them mounted plane of array, or sometimes referred to as global tilted irradiance, to measure the irradiance that falls on the surface of the PV module. Now, we have done some comparisons in Delft of different instruments. We have a Class A pyranometer, that's the highest class on the left. We have also considered an SP Light, Class C pyranometer, and an RT1, Class C pyranometer, which includes a back-of-module temperature sensor, and in addition also a working class reference cell. This is a photo of the setup next to PV modules. We have the different sensors mounted in the same orientation as the PV module. And when we look at some results of this work, which has been mainly done by Samit Karki, we see that there is a good linear, as expected, linear relation between the Class A pyranometer and the Class C SP1 pyranometer. And we have done a bit more in-depth analysis of these measurements in a so-called box plot. And here on the y-axis, you see the different sensors. And on the x-axis, you see the difference with the Class A, the highest class pyranometer. And then you can see in this blue, the interquartile range, which is giving 25% and a 75% distribution. And these whiskers, they give the 5% and the 95% distribution. So you see sort of the distribution, how much does this particular sensor deviate from the Class A pyranometer. And we see that there are differences. One of the photodiodes is spot on when it comes to the calibration, but all of them have some variation. When we dig a little bit deeper where this comes from, this variation, we find a number of things, and that is a relationship with the air mass, or the angle at which the sun is at a particular time of the day. We find a relationship with the temperature. We find a relationship with the spectral redshift of the solar spectrum at that particular time. And we can see that for some sensors, when you look at this graph, the air mass is here, the difference with the Class A pyranometer is there. There is a considerable relation with the air mass. And there's one sensor, the blue one, which has a fairly constant response, although still some variation exists. And we thought this is quite a complex interplay. We have temperature, we have angle of incidence, we have the spectral change, we have the air mass change. And we thought this could potentially be something where artificial intelligence can be beneficial. When the problem gets quite complex, then it can be beneficial. So work has been done on this, and we have tested artificial intelligence, and the way we did it is that the data was processed, usually a little bit of outlier filtering and filling of data gaps is done. Then this data was given as an input, and we used an artificial neural network for this, and we obtained the predicted output. When we dig a little bit deeper in how this worked, is that we had the input, we have a backpropagation neural network with a number of hidden neurons and the output, and then a cost function that looked at the output difference with the input was fed back to the hidden neurons. And then in an iterative way, this allowed us to train this network. Now, a bit more in detail shows you which kind of inputs we used in this example. And as an input here, we had the temperature, the air mass, which is sort of, it's dependent on the angle, the zenith angle of the solar irradiance, and the input from the Class C sensors. And then at the output, we had the Class A output to compare with. And then after training of the the network, we obtain the predicted output. And here you see what these sort of box plots of these outputs look like. And in the black, you see the let's say unimproved result, and in the red you see the same sensor but with the AI improvement. And in all cases, we see that the AI improves the measurement accuracy, and mostly sort of it shifts the difference, the median, closer to zero. And there's also a reduction in the variance, or let's say the precision is improved, but that, yeah, some variation still remains. That cannot be taken away completely, but that's a general picture that we see, that there is an improvement. Now it is still a question like, okay, how reproducible is this result if you would vary the location, or if you would vary the installation setup of a particular sensor. If you make a sort of a hand-waving guess at the uncertainty that sort of is left compared to a class A, we could come to roughly 2%. And if we go into the uncertainty of the sort of the the AI enhanced class C measurement result, then yeah, with a class A parameter, we start at roughly 2%. This can be calculated with a calculator that's available at the Google App Store from Kippenzonen, by which you can calculate the measurement uncertainty in the field. And we've seen from the previous slide that the rough estimate of the AI variation would be about 2% uncertainty. So if this could be included in a straightforward way, we would end up at roughly 2.8% root mean square error. So it's not as good as a class A sensor, but it could be better than it is. Now, as another follow-up question, where we have not worked on yet, is could we also make a class A parameter perform better? And then we were starting to think like, then we actually need to train it with the best irradiance measurement method available, with the lowest uncertainty, and that's with a tracker, with a parheliometer that measures the direct irradiance, and with a parameter or two parameters measuring diffuse. These are some pictures from Akiona Energy, and yeah, when we look at the uncertainty that we could achieve with a tracker solution, here we see a plot of the KS2 uncertainty over the day. We see that we could go below 1% or down to 1% with a tracker, and with a current class A parameter in the same site, we would be at roughly 2% at best. So yeah, the question is, can a class A parameter be trained with a tracker? And yeah, I'm afraid I'm having more questions than answers at the moment. So as to how to do this, and how to translate the training to different climate zones or tilt angles, and how low could the uncertainty go of class A parameters? So this is a question, and collaboration is welcome on this topic. Now that I said a few words about the irradiance sensor, I want to sort of zoom out a little bit and look a little bit more at the bigger picture, and then looking at the PV plant, and see if sort of this method for a non-ideal class C sensor, if it can be translated to a PV plant, where also you have a complex interaction of many different parameters, and even more complex than with a class C silicon parameter. And so we're going to look at the PV plant, and this is work that Sajjad Badalkhani has done. And when we look at the PV plant, we have a lot of things that determine the output. for now, we're going to focus on the weather and the environmental factors, such as the solar irradiance, the ambient temperature, the wind speed, the direction, the precipitation, and the soiling. Now, this is a concept of how to, independent of the irradiance, determine the performance of a PV plant, the performance ratio. And I'll quickly say a few words about it. It is sort of the ratio of the measured energy to the expected energy. And in formula form, it's here. And the solar irradiance determines to a large part the power output, but ideally the performance ratio would be independent of the irradiance level. But in a bit, we'll see that that usually is not the case. Another factor that greatly influences the PV plant power is the temperature, because when the temperature is higher, the PV cell efficiency drops, and then the PV plant generates less energy. We have the wind speed, which is the way that the PV plant modules can be cooled, thereby enhancing the efficiency. We have precipitation, which sometimes is beneficial in case there is soiling on the modules, but on other moments it can also block some of the irradiance, or in case of snow, it can block a lot of the irradiance. So there are different effects depending, amongst others, on the temperature. And of course, we have soiling directly, which absorbs the light, and it negatively impacts the efficiency of the module. Now, to see a little bit more, there's a case study done in Japan where we, from a plant, have obtained the calculated performance ratio over time, together with the global irradiance and the plane of array irradiance and the power output of the plant, and the ambient and the back panel temperature, as well as the precipitation and the soiling, and the wind direction and the wind speed. And when we make a correlation matrix of all these parameters, we get a picture as follows. You see the parameters on the y and the x-axis, and a red color indicates a high correlation, and a blue color indicates a low correlation. And I'm not going to go into all the details, but focus a little bit on the power output of the plant, and then we see that it heavily correlates with the irradiance as expected, but also with the rear of module temperature, the ambient temperature, and the wind speed. And with the help of these kind of correlation matrices, which are of course site specific, some sites will have other correlations, we can see a little bit which are the important things to measure in order to learn how the plant will be doing. Now we can apply these measurements also for a artificial intelligence algorithm, and that has been done with us, and you can see the results on this page. We have applied 4 different models, each with different inputs. So model number 1 has global irradiance as an input, and in this slide you see the classification as to how important is that particular input in that model. With one input, of course, the predictor has 100% importance. Model 2 has added also the temperature of the module and the ambient temperature and the wind speed. Model 3 has added soiling, precipitation. The 4th model has the most measurement parameters. When we look at the results of these models, we see different performances. So the performance is visible in the red line compared to the blue line. The red line is the actual power out, and the blue line is the predicted power out. And you see with the root mean square error on the top of the graph a numerical evaluation of how good the prediction is. And the first model does somewhat of a job, but not that good. And when adding more sensors and more inputs, you see that the root mean square error value gets better and better. So yeah, with model 4 having most of the predictors, then we get the best match between the predicted and the actual power output. As a small last sidestep, I will go a little bit into satellite data. So satellite data is also available. We've looked at satellite data from NREL and of a small track plan. And mainly we focused it, okay, if we compare this satellite data with ground measurements, how well do they overlap? And then generally, we can see that for all of the measurement parameters, that on a yearly basis, it can be somewhat accurate, a little bit depending on what kind of thing you're measuring, like for wind or for global, it's fairly accurate. For plane of array, somehow it is not that accurate, but yeah, for most of them, it's relatively accurate. But if we go to very short time frames, maybe down to 5 minutes, we can see that the satellite data becomes less accurate. And to come sort of to a bit of a conclusion is when we take ground measurement and satellite data and we feed that as input into a modeling or an AI approach, we can better predict the PV plant output. And when we can predict it and we see what the actual output is, we can start to see if something's going wrong in a plant, if somehow we have a large underperformance based on the prediction. And that, we believe, will help do a good job of maintenance and to show some of the instruments that OTT HydroMet makes for accurate measurements of these parameters. We have here the parameters. This is an overview of the different parameters for the different applications and the different accuracy classes. We have the dust IQ for accurate soiling measurement, and there is the series of weather stations which allow you to measure a large amount of meteorological parameters, including also back of module temperature with an external temperature sensor. So in summary, we've seen that Class C sensors are not as accurate and precise as Class A sensors. However, when using artificial intelligence, the performance of these sensors can be made more accurate and also somewhat more precise, but not as precise as a Class A sensor. And we would be interested to find out if we can use AI also to improve the Class A parameter performance. And a PV plant case study showed that with weather parameter input, you can get predictions of the plant power output. And with that, I'd like to thank you for your time and attention. We would welcome a collaboration or a partnership or research, and it can be reached at this email address. And I would like to acknowledge Samit Karki and Sayat for their input, and thank the organizers for giving the opportunity and this nice workshop.
Thank you very much, Mr. Marc, for this nice presentation. Thank you very much. So let's switch actually right now to some question. The first question is for Mr. Greg Smith. So it's our distinct honor and privilege to have with us Mr. Professor Greg Smith. So Mr. Greg, thank you, Marc, for your nice presentation. And I would like to ask you to comment on such measurements for bifacial module. So how it is best to do this, and what are the caution and caveat where can learn more about this issue.
Thank you. Yeah, nice to hear a question from you, Greg. Yes, this is a important topic, and my feel is it's still something that is developing. We have in this particular case study looked at a monofacial site, so not a bifacial site. In the monofacial site, it was the radiance and the back of module temperature in this particular location the most important. My assumption is that for bifacial, you would have to add the rear irradiance, and depending on the site, perhaps also soiling. But we have not studied this yet, so we'd be happy to learn in the future what the exact answer to this is. But this is my first thought, Greg.
Yes, thank you very much, Mr. Marc. The floor is yours, Mr. Greg, if you have anything to add. It's a pleasure to provide your participation with us today. The floor is yours, Mr. Greg.
No, I think thank you, Marc, for answering that. It's a great start that you've done, very exciting, and we look forward to further extensions and learning more.
Oh, thank you very much. Yes, thank you very much, Marc. I think if there is a question for other participants, if you have any question for Mr. Marc. So yes, there is another question for Mr. Munir Abraham. So Mr. Munir, thank you for your nice presentation. So the question is, and also is the following, and can also be used for automatic quality control for irradiation data.
Yeah, this is a good question. Yeah, unfortunately, I have not looked into that yet, but I know there's already a lot of work done on automatic quality control in the BSRN collaboration. So I think more of quality control can be found there. But I think it can be interesting to see, what can AI do in quality control of data. Yeah. So I take it more as a suggestion. So I don't have the answer.
Yes, thank you very much. Thank you very much. So, please, Munir, feel free to make a contact with Marc for further.
The answer.
Yes, thank you very much. Thank you very much. So, please, Munir, feel free to make a contact with Marc for further discussion and further question. Thank you very much. So let's switch for the next presentation with Mr. Muller. Are you with us, Mr. Moore? Mr. Thor?
Yes, I am. Here I am. Hello.
Yeah, hello. Thank you very much for joining us in this workshop.
The pleasure's mine. I'm happy to start.
So let's start with a first presentation of